All right, this is our very last video for simple linear regression. In this video, we'll be thinking about what can we say about y if we're at a particular or fixed value of x. This one should be a little shorter than the last video. Essentially, there's two main types of intervals that we'll be discussing. You'll need to be able to distinguish between those two types, and then for each, use jump to find the interval and then interpret it. As a reminder, this is statistical inference. We're trying to come up with intervals that describe the population values. So in order to do these things, you do need to go through the assumptions which were covered in the third video. They're all running together at this point. All right. So we're going to go to jump, and first we're going to fit y by x and add in our regression line. But then I want to just give you first an overview of the two distinct types of intervals that we're going to be covering in this lesson. So the first is called the confidence interval for the mean y at a given x. Remember, the population regression line describes this. What's the mean y at a given x? So we'll see this in a moment, but we're going to come up with these confidence bands. So these dashed lines here are where, in this case, we're 95% confident that the true population regression line belongs. Okay, so in the solid line here is our sample regression line, but it's just an estimate based on this one sample. So imagine that it's gonna, has a little room to wiggle. We're 95% confident that it's not going to wiggle beyond those dashed lines. Okay. Whereas the other type of interval we're going to do today describes where we think an individual value will fall. So this we're going to call the prediction interval, like predict where a particular gas station will lie. So again, with 95% confidence, notice these bands are a lot farther apart because naturally an individual gas station needs more room to vary than the mean value would. All right, so for 95% confidence, these bands we expect would typically contain 95% of the gas stations. All right, so let me show you how to get those bands in jump. All right, we're fitting y by x, same as we've done about 100 times at this point. So we're predicting sales based on the traffic. And I'm going to fit a line. And then it's by the red triangle next to linear fit where I can ask for those curves. So let me start with the confid curves fit. All right, if they're the close together ones, remember that describes the mean because the mean value, we're giving it some room to vary, but we don't think it's going to vary a whole lot. In this case, because of all the strength in numbers. Some may be higher, some may be lower, but according to the central limit theorem, everything will kind of move towards the middle for the mean. Okay, so we can then think about more closely examining any particular value of x on our graph. All right. On the other hand, if we added in confid curves in div, so this is the curves describing individuals. Those are going to be farther apart. Those are describing single gas stations in this case. I'm going to get rid of them for the moment because we'll focus on the confidence interval for the mean y at a fixed x first. All right, so we saw the intervals that we're going to be talking about using the dashed lines. So we're talking about the ones that were close together. So this is all backwards from what you see. So the formula is rather elaborate. It's a type of t interval, though. So there's a t critical value that's based on the confidence level. You notice, though, that they were curves. They weren't straight lines. So that unique shape is made possible by this somewhat complex equation here. The part I'm going to really focus on is this difference here, x naught minus x bar. So X naught is where we're going to identify and zoom in or focus in on a particular value of X. So we might say, for instance, what if we are talking about places where the traffic volume is 26,000 vehicles? So X naught would be 26. Or maybe we'll also try in a minute. What if we're in places where the traffic is 40,000 vehicles? Then X naught would be 40. So how does that affect the result that we might get? All right. So rather than compute this by hand, we're going to have Jump insert a formula into our data table. So I'll lead you through that in Jump. So from my fit y by x, I need to have the line in place, and it is. Then I'm going to go down to mean confidence limit formula. And now in my spreadsheet, I have two new columns. One showing the lower end of my confidence interval and one showing the upper. Okay. So these are being computed at each of the values of X, which is here traffic, that are present. But a nifty tool is you can go down to the next open row. So after row 80, we have an open row. And we can put in a particular value of X. So say we want to know among all places where there's 26,000 vehicles a day, what would be the mean gas sales? So I'm going to put 26 in the next empty row for traffic. All right, and then I will get the confidence interval that I desire. All right, so right here. And let's say we want to contrast that also to places where the vehicles are 40,000 a day. So I'll put in 40 as well. Okay, so I have another interval there. Well, before we interpret those, let's just see what they would look like. So I have this blue dashed line at x equals 26. So these confidence intervals that are in my spreadsheet, what they're describing is where, at x equals 26, what's the height of this lower dashed line? That would be the lower endpoint of my confidence interval. And what's the upper endpoint? So what's the height of this upper dashed line? And we can kind of see the width of the interval. In this case, it's more the height of the interval. So I actually copy pasted this bold section here and put it here so you can see how big it is. So that's representing the interval width. Now, if I go over here to x equals 40, notice due to the curved nature, the dashed lines are closer together. So that interval is narrower. It's, this big. So there's a clear size difference between them. So what's going on is you notice it's kind of a bow tie shape. So it's skinnier in the middle and gets wider at the ends. That is made possible by this term in the formula. So this formula says that the interval is going to be narrowest when we're at the mean value of x. And then it's going to be wider as we get farther away from it. Okay. So without looking up the mean value of x, it's going to be somewhere here in the middle. So 40 is not that far away from the mean value of x, but 26 is way at the fringes of the graph. So there's more uncertainty way out there. Whereas in the middle of the graph, near the average x, we have lots of data surrounding it on both sides. So it makes sense we can produce better estimates here. Okay, so if we were to grab those numbers that appeared in the new columns in the spreadsheet, when x is 26, these are the interval endpoints that I came up with. So we could say we're 95% confident that among all gas stations that have 26,000 vehicles passing per day, because this is a population mean, so among all of them of that type with x equals 26, we estimate that the mean sales would be between that number and that number, 1,000 gallons. Down here in orange, I have the same thing, just replace 26 with 40, and then different interval endpoints reflecting that with more traffic, we expect more sales. So notice both these numbers are larger than the blue interval up here. So that's because we expect to sell more gas on average. But the interval width, or how far apart are those two numbers, they're closer together than they were for the blue interval up here. Yeah. Now, my favorite, if I had to pick one, I like this next interval, which is the prediction interval for an individual value of y at a given x. Okay, because I think about, well, suppose I need to build a new gas station. What is my one new gas station going to do? The mean is nice to know and all, but if you're opening a sole proprietorship, you really want to know how your individual gas station is going to do. So this would be the interval described by these curves that applied to the individuals. So we saw they were a lot farther apart. So the formula is actually the same as the last one, except we're going to add in a 1 under the radical. So that makes it bigger. All right. And the default here is 95%. So, we would expect 95% or so of the gas stations to be within the bands. And that seems to be the case. There's only a couple that are outside. Okay, so going back to jump, let's get rid of these curves that are for the mean, and let's add in the curves for the individuals. And then just for a fair comparison, let's use x equals 26 again, and also x equals 40. One more thing we need to do. We need to add in the formula for the individuals. So that one is going to be called indiv confidence limit formula. All right, so we're getting a lot of columns here, so just pay attention to what they're titled. So the first two that we added in were for the mean. So they say mean right there in the title. I'm going to ignore those for now and scroll over to the individuals. And notice the 26 and the 40 that I put in earlier are still there. So I don't need to enter them again. I just scroll over and see my new results. All right, so for x equals 26, my interval now spans all the way from 1.743 up to 7.891. So a lot wider than it was when we estimated the mean. And then I have another interval here for at x equals 40. Now, it's hard to tell, but there is still a slight bowing of these lines. They're not exactly parallel. So again, they are going to be the closest together near the middle, near x bar. So the confidence interval in purple here at x equals 40 is going to be just a little bit narrower than the interval at x equals 26, although not as to great an extent as with the mean, which was clearly more curved. So here's those intervals. So I grabbed the numbers that we just saw a moment ago on the spreadsheet. So this time our interpretation is going to reflect the fact that this is where we think an individual gas station is going to be. So you shouldn't use the word mean at all or average. This is the one case where we actually do want to focus on a single individual. So I could say here for at x equals 26, we're 95% confident that a gas station with 26,000 vehicles passing daily will have daily gasoline sales between these two amounts. All right. And hopefully you see how that could be really useful if you're placing your new gas station and you want to know how much, how many tanks will you need to fit the demand. You can now have a pretty good handle on what, at least with 95% confidence, how much would you sell? and not just an average for the whole population, but how much would your specific station sell? All right. If your location had 40,000 vehicles, like the one down here in purple, then you'd need more tanks. But now you know you can be 95% confident that that's the amount that you would sell. It'd be somewhere in that interval. So the default is you get 95% confidence intervals, but we can ask for a different value. So down by linear fit, the same place that we asked for those intervals in the first place, you can ask to set the alpha level. So 95% corresponds to 0.05. If we want 99%, that corresponds to 0.01. And actually, hopefully you just saw it, my bands moved farther apart for 99% confidence. All right, so we'd expect now that 99% of the dots are within the individual bands. And in this case, it looks like actually all 100% are, but that's really close to 99%. Okay. All right, so now if we added in either the formulas for the mean or for the individual, they would now say that they're the 99%. Okay. And like all other intervals, the more confident we want to be, the farther apart our endpoints will lie. All right, so why don't you give it a try? Go ahead and open up the muscle spreadsheet. And how about you come up with 90% intervals for 50-year-old men? First, the mean of all 50-year-old men, and then for an individual 50-year-old. Okay, I'll see you back here when you're done with that. All right. So to get those intervals, we fit y by x using age to predict the lean muscle mass. Fit y by x, fit line. And then if we want 90%, we would change our alpha level to 0.10, because that's the complement. All right, so if we're interested in the mean among all men who are 50 years old, we would go to the mean confidence limit formula. And I'll just go down to the next open row and put in an age of 50 years. So we can be 90% confident that among all 50-year-old men, their mean muscle mass or mean lean muscle mass is between 91.8 pounds and 101.9 pounds. If you want to see that, we could add in the curves. Curves fit, basically the one that doesn't say individual, that's the mean. And to visualize it, we'd be at 50 years old, and our two endpoints would be the upper at 101.9 and the lower at 91.8. Now, if we're instead talking about an individual man who's 50 years old, suppose your dad is 50 years old or something, how much lean muscle mass does he have? We're going to see an interval that's much wider. And to get the endpoints, I need to add in the formula for the individual. And now we can be 90% confident that your dad or whatever 50-year-old man we're talking about has a lean muscle mass between 81.3 pounds and 112.4 pounds. All right, so that is it for simple linear regression. We just used formulas to come up with intervals for the mean value of y at a fixed or given x and the individual value of y at a given x. So for either of these type of problems, I'm going to have to tell you what x is, like a 50-year-old man or a location with 26,000 vehicles passing by. All right, so you should be ready now for homework 9. And this is the last lesson covered on midterm 2. So remember that midterm 2 is going to cover chi-square tests. We did 2 types of those. Then we did one-way ANOVA, and then all of this correlation and simple linear regression. All right, happy studying.